Welcome back to Linear Algebra. I'm Dr. Jeff Groh. Today, we're going to talk about linear transformations. We'll begin with the definition. Let V and W be vector spaces. A linear transformation is a function. We'll denote it by T. Its domain will be the vector space V, and the codomain will be the vector space W. Notice I didn't say range. Range is everything that actually gets mapped onto. W is mapped into. That means the function T may not map to everything in W, but at least it maps to some subset of W. But it's not just a function between vector spaces. It has to satisfy two very important properties. Such that 1, T of U plus V is equal to T of U plus T of V. For functions that are not linear, students often try to apply this kind of algebra and do so inappropriately. For instance, if the function squares x, y equals x squared, then a plus b quantity squared does not equal a squared plus b squared. There's that 2ab term in the middle. Linear transformations satisfy this very simple property. T of u plus v equals T of u plus T of v. But there's one more property. T of a times u is a times T of u. So constant scalar factors of u can factor out of a linear transformation. Now, these seem like very simple functions, but you're going to see that there are very many important applications for linear transformations. To show you just how serious we are about this concept of linear transformation, I want to give you an example. Let T of f be the derivative. Now, what are the domain vector space and codomain vector spaces? Well, the domain vector space will be the vector space of all differentiable functions, and the codomain looks like maybe functions that are derivatives of differentiable functions. So consider this. 1. If you take T of f plus g, do you get T of f plus T of g? And the answer is, well, you know that the derivative of the sum is the sum also. Is it true that T of a times f equals a times T of f? Well, isn't it true that the derivative of a constant times f is a constant times the derivative of f? You can see that the derivative is a linear transformation, and we are very serious about the derivative. For another example, suppose T of f is the integral from a to b of f of x dx. Well, what is the domain vector space? The vector space of maybe one-time integrable functions on the interval a, b. And what is the codomain? Looks like the set of real numbers, which is a vector space, R1. Does this satisfy the two properties of linearity? Is it a linear transformation? We can check. T of f plus g is the integral from a to b of f of x plus g of x dx, which you know satisfies is equal to the integral of f of x plus the integral of g of x, which is t of f plus t of g. It satisfies the first property of linearity. What about the second property? Second, t of k times f. That's the integral from a to b of k f of x dx, and you know that constant factors pull out of integrals, which gives you k times t of f. That means that the definite integral is a linear transformation. A linear transformation T mapping V into V, a vector space into itself, has a special name. This is called a linear operator. So linear operators map a vector space into itself. As an example, suppose I have a function. I'm not assuming that this is a linear transformation to begin with. And it inputs elements in R2, and it outputs things like, let's say, 4x plus 3y minus 2x plus y. I ask, is this a linear transformation? You can see that this function takes the matrix 4, 3, negative 2, 1 and multiplies onto the vector xy. In other words, T of V is the matrix 4, 3, negative 2, 1 times the vector V. Is such a thing T of V equals a matrix times V, a linear transformation? We need to check the two properties of linearity. Check it out. T of U plus V is going to be A times U plus V. Matrix multiplication is distributive. So you get AU plus AV, which is T of U plus T of V. That checks the first property of linearity. Now, what about T of K times U? What happens to the constant K? Well, it's A times K times U. Scalars commute with everything, so we can bring the scalar K out front. And that gives us K times T of U, because what does T do? It multiplies by A. This verifies the second property of linearity. Therefore, T, which maps R2 into R2, is a linear operator. More generally, if T of U is A times U, where A is M by N, then T will map Rn into Rm. If the function T is defined by multiplication by a matrix A on the left, then T is a linear transformation. As another example, suppose I have the function T of xy equals 2x plus 3y, 4x plus 2y plus 1. Is this a linear transformation? Well, how about this? What happens if we take xy and multiply it by k? That's going to be T of kx, ky, which is 2kx plus 3ky, 4kx plus 2ky plus 1. Now, while you can factor k out of the first coordinate, you can't factor k out of the second coordinate because of the +1, which means you can't factor k out of the linear transformation. Therefore, this is not a linear transformation. That +1 kills it. There are certain facts that we can prove about all linear transformations. Let T map V into W be a linear transformation. Then T takes the 0 in V and outputs the 0 in the vector space W. Let's work on this. Let's prove this. Take T of 0. That is T of 0 times 0, which is 0 times T of 0. And if you rescale a vector by the 0 scalar, you get 0. But this one will be the 0 in W, the codomain space. As a quick example, suppose T of xy outputs something in the vector space of 2 by 2 matrices, e to the x, 0, 0, e to the y. Is this a linear transformation? Well, if you take the 0 vector in the domain space, you end up with e to the 0, which is 1. E to the 0, that's 1. And that is not the 0 vector in the vector space of 2 by 2 matrices. Therefore, we deduce that this is not a linear transformation. Recall, so A transpose reverses the roles of rows and columns. So if you take Aij transpose, you end up with Aj reversing the role of rows and columns. For example, if I have 1, 2, 3, 4, 5, 6 transpose, what I get is 1, 2, 3, 4, 5, 6 in this way. Reversing, taking the first row and making it into the first column, the second row into the second column. My question is, if T of A equals A transpose, is this a linear transformation from the set of m by n matrices into the set of n by m matrices? Well, we can check the two properties of linearity. In particular, T of A plus B will be A plus B transpose. The transpose does distribute across sums, and that gives us T of A plus T of B. Also, T of K times A is K times A transpose, which is K times A transpose, and that's K times T of A. So the answer is yes. It's possible to express the two properties of linearity as one. The function t mapping v into w is a linear transformation if and only if the following property holds. T of ku plus v equals k t of u plus t of v. One property, not two. The proof is an if and only if proof, so you have to prove the implication in both ways. So if we assume that T is a linear transformation, then because it satisfies property 1, it satisfies the first property of linearity. It's T of Ku plus T of V. And because it satisfies the second property of linearity, you get K times T of U plus T of V. We now need to prove that the implication goes the other way. If this one property holds, then the two properties of a linear transformation holds. So we're going to assume that this property holds. Setting K equal to 1, we have T of 1 times U plus V, which is T of U plus V, is 1 times T of U plus T of V, which is T of U plus T of V. So if you satisfy this one property, if you just set K equal to 1, then it will satisfy the first property of linearity. We need merely check that it satisfies the second. To see that it satisfies the second property of linearity, we'll set V equal to the 0 vector in the vector space V. Then T of Ku plus 0 is T of Ku. This must be K T of U plus T of the 0 vector in the vector space V. By the last theorem, we know that this maps to the 0 vector in W. And if you add the 0 vector to anything, it leaves it alone. And that completes the proof. This last theorem allows us to check only one property, thereby shortening our proofs of linearity. Now, it turns out the representation of a vector by its coordinates is a linear transformation. Consider T of V equals the coordinates of V relative to some basis, where V is a basis for some vector space V, where V is an element of that. Then we will show that T, which maps our vector space into Rn for some n, is a linear transformation. This will have important consequences. This tells us that instead of dealing with some vector space, we can always transform using coordinates to Rn, and that transformation is linear. So how do we prove this? This will be a theorem. In our proof, we'll let the coordinates of U relative to a basis be A1 through AN, and the coordinates of V relative to the same basis be B1 through Bn. Then what does that mean? That means U is A1, let's see, the elements of the basis we'll call V1 through AN, Vn, and V will have coordinates B1, V1 through Bn, Vn, where B is the basis, the ordered basis, V1 through Vn. Then what about Ku plus V? Is that not Ka1 plus B1 V1 through Kan plus Bn Vn by the basic properties of a vector space, the distributive law, the commutative and associative laws? And that means that the coordinates of ku plus v relative to the basis are ka1 plus b1 through kan plus bn, and we can rewrite that as k times a1 through an plus the vector b1 through bn. And it follows then that we get k times the coordinates of u in b plus the coordinates of v in b. Therefore, T is a linear transformation. Now, a linear transformation is completely determined by its action on a basis. In other words, if I know what a linear transformation does to elements of a basis for the domain space, then I can figure out what that linear transformation does for anything else. And it's because if I take some t of v, v can be expressed uniquely as a linear combination of elements on the basis by the properties of linearity. I get c1 t of v1 through cn t of vn. So if I've already determined what the linear transformation does to elements of the basis, I can figure out what it does to anything else by taking the appropriate linear combination. Here's an example. Suppose that T maps R3 into R2. T of 1, 0, 0 is, say, 1, negative 1. T of 0, 1, 0 is 2, 3. And T of 0, 0, 1 is 4, negative 3. Then find T of 0, 2, 3. How do we do that? Well, what is T of 0, 2, 3? It's T of 2 times 0, 1, 0 and 3 times 0, 0, 1. That means we'll take 2 times the value on 0, 1, 0 and 3 times the value on 0, 0, 1. That gives us 4, and 12 is 16, and then 6 minus 9 is negative 3. The value of a linear transformation is completely determined by its action on a basis. Linear transformations have their own algebra. If T maps V into W, and let's say S maps V into W, are linear transformations, then KT plus S is a linear transformation. We can combine linear transformations to make other linear transformations. The proof is rather simple. All we have to do is take KT plus S and apply it to U plus V, which we can see is going to be KT of U plus V plus S of U plus V, which is K times T of U plus T of V plus S of U plus S of V. By the commutative and associative laws, we can rewrite this as KT of U plus S of U plus KT of V plus S of V. But that is KT plus S of U plus kt plus s of v. That's the first property of linearity. We need to prove the second. To prove the second property, suppose we have kt plus s acting on au. That's kt of au plus s of au. Because t and s are linear transformations, the a can be brought out. And that a can then be factored out of the entire thing. And that gives us a times kt plus s of u, the end of the proof. As you can see, we're kind of treating the set of linear transformations from v to w as though each linear transformation itself is a vector in some larger vector space. This last theorem proves that the set of linear transformations from v to w is closed under addition, and it's also closed under scalar multiplication. Linear transformations are associative, and what is more, there is a zero linear transformation, the function that maps everything to zero. That is a linear transformation. It satisfies the property of 1. 1 times a linear transformation is that transformation. It's associative under scalar multiplication. You can see there are distributive properties, all the properties of a vector space. We'll make some notation first. Let L, V, W be the collection or set of linear transformations from V into W. We have the following theorem. This set of linear transformations is a vector space. There is one more basic operation that we have to add to all of this, and that is function composition. Let's suppose that u, v, and w are vector spaces T maps u into v, and S maps v into w. The linear transformations. Then S composed with T, which maps u into w, is a linear transformation. So function composition will lead to additional linear transformations. Let's take S composed with T of ku plus v for vectors u and v in the vector space U. That gives you then k t of u plus t of v, and that is k s of t of u plus s of t of v, which is by definition the composition. So we get k s composed with t of u plus s composed with t of v, and that's the end of the proof. A typical application might be on something like this. Suppose we're looking at the differential equation. Let's say y double prime plus 3y prime plus 2y equals 0. Set L of y to be y double prime plus 3y prime plus 2y. I ask you, is L a linear transformation on the space of second-order differentiable functions? Well, let's find out. L of y1 plus y2 will be y1 plus y2 double prime plus 3 y1 plus y2 prime plus 2 y1 plus y2. We can distribute the derivatives, giving us y1 double prime plus 3 y1 prime plus 2y1, y2 double prime plus 3 y2 prime plus 2 y2, and that's L of y1 plus L of y2, the first property of linearity. We need merely check the second property of linearity to prove that L, defined by this combination of derivatives, is a linear transformation. If we had used that theorem and one equivalent property to the two, we'd be done already. Here we get ky double prime plus 3, ky prime plus 2, ky. Constants pull out of derivatives, so we get k times 3y double prime plus 3y prime plus 2y, and that is k times L of y. It follows then that L is a linear transformation. That means that the linear transformation L is completely determined by its action on a basis. The solution set to this differential equation will end up being a vector space, and so if we find a basis for solutions to that vector space, we can determine every solution by the action of the linear transformation on that basis. We can find every solution by taking linear combinations of that basis. We complete that program of finding the complete solution set by looking at linear combinations of a basis for the solution set in our course on differential equations.